Section 3.4, Graphing Linear Equations in Standard Form. Standard form is another way to look at the equation of a line, and standard form looks like ax plus by equals c. Now we'll look at a lot of equations that are in almost standard form, but to be in true standard form there are 4 requirements. First of all, a, b, and c, these coefficients and this constant are all integers, so no fractions, no decimals. Second requirement is that a and b are not both 0. It's okay for one to be 0, but not the other. If both are 0, we'll see it doesn't really make any sense. The third requirement is that a is not negative. All right, b could be negative, c could be negative, but not a. And then the fourth and final requirement is that a, b, and c have no common factors other than 1. We'll see an example now at the bottom of 4 equations that would violate each requirement, and we'll show how to fix them. In the first example, you see that we have 2/3 x plus 7y equals -1. It looks like standard form because it's a number times x plus a number times y equals a number. But it's not in standard form technically because a, b, and c have to be integers, and 2/3 here is a fraction. To fix that, I'm going to have to multiply everything by the denominator. So I'm going to multiply everything by 3. And when I do that, I have to make sure that I distribute that 3 to both parts of the left side of my equation. The 3 will multiply by the 2/3, resulting in just 2x. Plus 3 times 7y is 21y, and 3 times -1 is -3. And so that there is actually in standard form. It's the same equation, just looks like it's technically in standard form there. The second example, which is 0x plus 0y equals 8, this violates the second rule. And we'll see it just really doesn't make any sense. 0x is the same thing as 0. 0y is the same thing as 0. And 0 plus 0 is 0. And certainly 0 does not equal 8. So this just doesn't make any sense at all. This is not something that you'll ever really see. It's just something you should keep in mind that you're not going to end up getting 0 for both a and b. Looking at the third example, where we have -x plus 5y equals -6. This violates the third rule because a is my coefficient of x, and here it's -1. But a is not supposed to be negative. The way to fix that is to multiply everything by a -1. Just like before, when I multiply by a negative, or multiply by anything on the left side, I'm going to distribute it to both the x and the 5y. So that's going to turn it into a positive x minus 5y, and -6 times -1 is positive 6. So now that's, again, the same equation as what I started with, but it's actually in true standard form. And then finally, the last thing, I have 2x plus 8y equals 6. That's not technically in standard form because 2, 8, and 6 all have something in common. They can all be divided by 2. And that's exactly what I'm going to do here. I'm going to divide everything by 2, which is going to reduce my equation to look a lot nicer. X plus 4y equals 3. So what we've done here is we've just taken 4 original equations, and one of them doesn't really make any sense. It's an equation that's pretty much nonsense. But the other 3 we were able to rewrite into equations that are equivalent but are in true standard form. Okay, so that's just a technical thing. Now let's see how we can use this. The most convenient and easiest types of functions to look at here are equations of vertical and horizontal lines. I mentioned before that it's okay if either a or b is 0, just not both. So in this first example, I have 1x plus 0y equals 6. You see it's in standard form. Now, 1x is the same thing as x, and 0y is the same thing as 0. So this is really just the same thing as x equals 6. X equals 6 is going to be a line that satisfies that equation x equals 6. Every point on the line has to make that equation true. meaning every point on the line has to have an x value of 6. That's going to make it a vertical line. You can see here that I go to the x value of 6 and I draw a vertical line. All of the points on this line have an x value of 6. And so if you ever get x equals a number, that's what you're going to be looking at here in terms of graphing. Very similar thing on the second equation, 0x plus 2y equals 7. Well, 0x is just the same thing as 0, so that doesn't really matter. So I'm really looking at 2y equals 7. And while that's in standard form, I can make it a little simplified or easier to work with by making it y equals 7 over 2. Now that's not technically standard form, but it's going to be good enough here. If we get y equals 7 over 2, which is the same thing as 3 1/2 or 3.5, we can look at the graph of that, and instead of being a vertical line, it's going to be a horizontal line. And so what you see here is I would go up to 3 1/2, so halfway between 3 and 4, and draw a horizontal line. The y value on each of these points that makes up this line is 3.5, and so that's how I know what I'll have there. Again, anytime you get y equals a number, you're looking at a horizontal line. What if one of our coefficients isn't 0? That's when it's more interesting. Let's take a look at those. So one thing that's really convenient with standard form is that we can use the x and the y-intercepts. Now the x-intercept is the location where a graph crosses the x-axis. The x-axis is this horizontal axis. And so this point right here, 6, 0, is where the graph crosses the x-axis. That's why I've indicated that that's my x-intercept. At your x-intercept, your y will always equal 0. Your y-intercept is very similar. It's wherever your graph intersects or crosses your y-axis, the vertical axis. You can see here that's at the location 0, 4. That's our y-intercept. And for the y-intercept, the x will always equal 0. Now these are the particular intercepts for the equation 2x plus 3y equals 12. The way that we know that this is right is we can plug in each of those points into the equation and we'll see that it's true. For example, if I plug in the y-intercept, I have 2 times 0 plus 3 times 4 equals 12. And we'll see very quickly that that's 0 plus 12 equals 12, which is right. Same thing would be true if I plugged in 6, 0 for x and y, using the x-intercept. We're going to get 2 times 6 plus 3 times 0 is 12, and that's just 12 plus 0 equals 12, which is also correct. So because those are 2 points that are definitely on the line, we can connect them by going along the line here and graph our entire function. So how do we go about finding those 2 points? So the first thing that we're going to want to do is we'll look at our equation, 3x minus 5y equals 30, and we're going to first find the x-intercept by setting y equal to 0. So I'm going to start by saying y equals 0, and that's going to get plugged into my equation. 3x minus 5 times 0 equals 30. The minus 5 times 0 is going to disappear because that's just 0. So 3x equals 30. X, therefore, equals 10. Using x equals 10 and y equals 0, we can get our first ordered pair, 10, 0. That's step 1. Step 2 is to find the y-intercept. We're going to do the same process, but we're going to have x equals 0 here. When x equals 0, I'm doing 3 times 0 minus 5y equals 30. Now 3 times 0, just like the 5 times 0 before, disappears, but that negative has to stay with me. Negative 5y equals 30. Then dividing by negative 5, I get y equals negative 6. Using these two coordinates, x equals 0, y equals negative 6, I'm going to get my other ordered pair. A common mistake is to put these two numbers together and get the ordered pair 10, negative 6. We don't want to do that. Remember that for the intercepts, either your y or your x will have to equal 0. Now that I've done that, I'm just going to plot these 2 points on a coordinate grid and draw a line through them. And so you can see here, we just put 0, -6, 10, 0, connect the line through them. And that's the graph of that equation. Every point on there will satisfy this equation here. All right, pretty straightforward stuff. You're just using zeros, which are really convenient numbers to work with. All right, let's take it one step further. All right, so let's take a look at a really important real-world scenario, buying Chicken McNuggets. We have two options. We can purchase Chicken McNuggets in packages of 6 or in packages of 20. Now, let's say we want to order 240 total pieces of chicken. We could actually use a linear equation to model our options because we have different ways we could do it. This linear equation, 6s plus 20l equals 240 is what we would need. 6s would refer to the number of pieces of chicken we get from getting s small orders. The s there is for small. And the 20l would come from the amount of chicken we'd get from a large order. So if we got, say, 3 large orders, that would be 20 times 3, which would be 60 pieces from that. If we got 4 small orders, that'd be 6 times 4 is 24 pieces of chicken from that. And we want to add those two numbers together to give a total of 240. So what we can do with this is we can actually find the intercepts in order to do this. Now, I don't really have an x and a y-intercept here. We have an s and an l-intercept, but we can go about it the exact same way. Let's first start by making s equals 0. All right, now if s equals 0, then I have 6 times 0 plus 20 times l equals 240. The 6 times 0 will disappear. I'll be left with 20l equals 240 divided by 20. I get L equals 12. And so that's going to give me an ordered pair. I'll put the 0 first. That'll give me 0, 12 is an ordered pair. And I'll find the other intercept here by making L equals 0. And that'll give me 6s plus 20 times 0 equals 240. The 20 times 0 basically disappears. I'm left with 6s equals 240, and divided by 6, I get s equals 40. And so s was first in my ordered pair, so I'm going to do that again. 40, comma 0 is my point. So I have two intercepts here, 0, negative 12, which is, 0, positive 12, which is going to be my y-intercept, and 40, 0 is going to be my x-intercept. All right, so let's graph those 2 points and connect them. Let's take a look at that graph. So you have here the graph, and we can see exactly these 2 points, the 0, 12, and the 40, 0, and we've connected them. And I've identified 3 other points that are on the graph. And so what we have here is we have a lot of different options. The graph actually shows us all the different ways we could get 240 total pieces of chicken. The x-axis I've labeled 6 piece, my y-axis 20 pieces, small or large. If we think about a few different things, we have a few points to consider. First we have the point 0, 12. What that would correspond to is if we got 0 small orders, or the 6-piece orders, and 12 20-piece orders. That would give us the 240 total pieces. The other one would be the other intercept, 40, 0. That would be 40 6-piece orders and 0 20-piece orders. That would cover our 240. So these two scenarios are both really choosing only one of the options. Using only the 6-piece or the 20-piece. But I have 3 other pieces highlighted, and really those are if I mix it up a little bit. For example, I could get 10, 9 here. This corresponds to getting some 20-piece, some 6-piece. Specifically getting 10 6-piece orders and 9 20-piece orders. The 10 6-piece orders would be 60, and the 9 20-piece would be 180. Together that gives us the 240 we want. Now, despite what we have here, where we've drawn the line, realistically we actually would have a discrete domain, and we wouldn't actually extend it into beyond there, because that would mean negative values for X or Y, and that's impossible. We can't order negative orders of chicken. But these points right here that are highlighted and labeled, those are actually really your only points that we're really going to have. So because we can't order parts of an order. So it's something to think about. This is an example with a discrete domain, because you can't order, you can only order whole number packages of 6 or 20. But that's what this graph represents. The different options are the ones that are the nice whole numbers. And there you go. Hope that this makes a lot of sense.